All right. So what we're doing today, thank you, is starting chapter 1. So we're starting chapter 1 of Algebra 2. Now chapter 1 is going to be a little different than the rest of the other chapters in that what we cover from section to section is going to jump around a little bit more. So today we're talking about intervals, number types, set notation, all this here. Later on we're going to talk about systems, and it's just going to jump from category to category. And this is the only chapter that's going to do this. And most of what we cover in this will not show back up again. But again, I think it's something good to know, good to have seen, so we're going to go over this here. Now the rest of the chapters are going to hit a specific topic, concept, and it's going to stick with it through the whole chapter. It's going to actually thread together and be cohesive. So again, I just give that kind of heads up because from section to section of this chapter, it does deviate a little bit. Because 1.2, our next section, is going to talk about parent functions, or different types of parent functions. So y equals x is the parent function for every equation of a line. Y equals x squared is the parent function for any quadratic. It's just talking about parent functions. So I'm just saying that not to scare you, I'll just let you know. So from section to section for this, it's going to be a little different. It's not going to be uniform in nature. But looking at 1.1, intervals and set notation. Well, the first thing we need to talk about is what is a set. Now there's different types of sets that we can have. Mathematically speaking, a set is a collection of objects. Braces are used to list a set's members. So if we're just talking about a set, a finite set, we will use braces and list the set's members. Or we can use words, it's a little interchangeable. So a set is just a collection of objects. As we could say a set of desks. It could be actually physical objects, or it could be more abstract. So right there at the top, so next to set. You're good? So just a collection of objects. So example 1, 2, 3. We can put a brace. 1, 2, 3. That is a set. Now we could also say positive even numbers. So the first thing we would do is put a brace. And what is the first positive even number? 2. Why do we not include 0? Because 0 is neither positive nor negative. It's not positive or negative. And it's actually not odd or even. It's pretty much neutral, yeah. So we can do 2, 4, 6, 8. Is there any way for me to write all of the positive even numbers? No, it's going to continue on, yes? Because I could say 10, and then we can do dot, dot, dot. So the dot, dot, dot just signifies that it continues on in this pattern indefinitely. So as long as we establish a pattern, 2, 4, 6, 8, dot, 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 we have the rest of them. So we would need the dot, 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 because if we just put a brace, we're just saying it's 2, 4, 6, 8. Or 2, 4, 6, 8, 10. It's just that set. We need the dot, dot, dot to tell whoever it is if that is going to continue on forever in that pattern infinitely. So if we just wanted the positive numbers, we would say 1, 2, 3, or 0, 1. Well, yeah, 1, 2, 3, 4, 5, 6, dot, 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 dot. And it would keep going. Does that make sense? Questions on this so far? Now, there are specific sets of numbers, groups of numbers, and we call them number types. So this is the first year I actually have this all on one slide for your notes, in your staff has been broken up into individual slides. So in the very center, we have what we call the natural numbers. And I did not get this rhyme. I actually heard this somewhere else, because natural numbers are naturally the numbers you count on your hands and your feet. Yep, so it's going to go in the far center box. So we're going to fill this out as we go. So the spot where you see all the little boxes, the smallest of that one, over one. Yeah. Yep, you got it right. So that one box, a little bit below it. I would leave that blank, because there is actually a group that contains all of them. Yes, right there. Yep, first box right there. Because the one that contains all of them, a little bit of a spoiler, is called the real numbers. So what goes in the space between that box and the other one is going to be the real numbers. The natural numbers are just our counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, going on. Now, mathematically, we do have a symbol. It's an N with 2 lines. Is the natural numbers. Now, mathematicians use this as a way to signify what type of numbers we're talking about, kind of what group. We talk about the natural numbers, which is an N with 2 lines. And we've used these before, yes? Natural numbers? Well, we do have a bigger group of numbers, which we call the whole numbers. Anybody notice the difference between natural and whole? 0. That's the only thing the whole numbers add, is 0. And if you notice, we're slowly building a number line, all of our numbers. So we started with natural, which is 1, 2, 3. We have whole numbers, which just adds 0. And we will start adding decimals here in a second. Anybody have an idea what the whole number symbol is? There isn't one. Oddly enough, because most of the time when we talk about numbers and adding 0, we kind of skip past whole and we go to integers. So they'll more likely reference it as the positive integers than they will whole numbers. Yes. So natural numbers is N, obviously. Integers, the symbol is going to be Z. Makes a lot of sense, yes? Not really. Yeah. Part of the reason is the other box that we haven't got to yet, there is a set of numbers called irrational. We'll get there in a minute. It came before integers. So irrational took I, so integers had to have something else. But integers give us the positive and negative. And we're kind of building this number line up, because we started out with just positive, our counting numbers. We added 0. Now we add the negatives, the opposite of our natural numbers. Now we need to start adding in some of our decimals, yes? Which would be our rational numbers. These are any number that can be written as a ratio. Any number that can be written as a fraction. Yes. So 0.25 is the same as 1/4. Anything that can be written as a fraction is rational. And rational is Q. It feels like it should be R, yes? But something took it first. Because that's taken by our real numbers. So far we've got positive, 0, negative. Now we've gotten fractional, yes? But we still have not covered every possible decimal point. Because there are such numbers that cannot be written as a fraction. You also covered one in geometry. It was pi. Because pi is not rational, it is irrational. So all of our irrational numbers. So the first one is phi. 1.6180339 is another irrational number. And the other one is e. You have not used e. We won't ever use phi in this class. Algebra 2, or really in high school for the most part, you are not going to use phi. E will come up in the spring. It's dealing with exponential functions. This is where e comes into play. Now, there are other irrational numbers. Square root of 2. Anytime we take a radical of a number and it doesn't come out nicely, it is going to be considered irrational. So square root of 2, square root of 3. Square root of 4 is not irrational, because what is the square root of 4? 2. So it's not irrational. The sixth root of 2 is irrational, because we get this non-ending, non-terminating decimal point. Questions on these so far? And irrational is our I with 2 lines. It's kind of interesting that they came up with the concept of an irrational number before they came up with the concept of a negative number. And it's not so much that they didn't come up with it or didn't have it, especially when they had the rest of these. It's more that we thought of it as the opposite of the additive inverse. Instead of going 2, we went the opposite of 2, not negative 2. Because the concept of negative came way later. And now, as I said at the beginning, we do have something that encapsulates all of this, and those are our real numbers. The real numbers is all of it, everything. And it is our R with 2 lines. The real numbers is R with 2 lines. So when we talk about this, we're talking about all of these numbers here. But that does beg the question, doesn't it? If all these are considered and we talk about them as being real numbers, that means there also must be what? Fake numbers, non-real numbers. And we call them complex. There are such things as complex numbers. And we will cover them in Algebra 2. Because we'll talk about these complex numbers, these numbers that don't work, or not real. And most of these complex numbers, where you see them most in real life, is dealing with electronics, the potential for energy to flow. If something is turned off, is there still potential for energy to flow? Yes. So we need a way to kind of describe that, and it goes into the complex plane. So there are such things as complex numbers, but we will table that for now. It will come up later. And interestingly enough, the symbol for complex number is a C with a line. It's complex numbers, but we won't have to worry about that symbol or it coming up. Because when we start talking about complex numbers, we're not going to talk about them as sets or trying to describe the set of complex numbers. So, let's look at these first few here. And we're going to do some examples. So it's number 3, the set of whole numbers less than 10. And there's different ways we can write this. So we could write it increasing or decreasing. What is the smallest whole number? 0. What's the biggest? That's it. The set of whole numbers less than 10. Now, if you wanted to write it the other way, that's perfectly fine. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Both will work. They're both a set. Yep, we can shuffle them, we can rewrite them however we want, because we're not going to say that each one is unique. There are certain operations or certain types of mathematics where that would be the case. Where we're talking about a set pair, two numbers are unique, that 1, 0 and 0, 1 are not the same part of the set, then order would matter, but here, order doesn't matter, as long as they're all there. Now, I would say if we're talking about the ... we're continuing on indefinitely, order does matter, because we're setting up a pattern. The set of odd whole numbers less than 24. So this one, that is a good question. Would we? Yes. So the question was, would we add 0? And we would not, because 0 is neither odd or even. So it's neither. So 0 would not be included. Our first odd number is 1. Then we would have 3, 5, 11, 13, 18. And that's it. And oddly enough, 1 is not the first prime number either. The first prime number would be what? 2. 2 is the first prime number. Because 1's not prime, because for it to be prime, its only factors are 1 in itself. So 1's not considered prime. And 2 is also the only prime even number. Questions on this here? The next thing we're looking at is a subset. A subset is, okay, that's on. I need to fix that. A subset is a set that is a set that is part of a larger set. All of one is contained in the other. A subset is a set that is part of a larger set. And we'll look at a few examples, and I'll talk about a few examples of this here. As you're writing that down, if you finish, you can look at A and B that are listed there. If you notice on your paper that all the numbers in A, all the elements are part of set A, are contained in set B. 1 is contained in both A and B. 3, 15, 20, 27, they do have both. So what that means is A is a subset of B, because everything in A is contained in B. So A is a subset of B. It doesn't just have to be with numbers. We could say that this math class, this room 12, is a subset of the high school, because every part of this room is contained within the high school. We can say that the high school is technically a subset of Colcord, because all of the high school is contained in Colcord. Colcord is a subset of Oklahoma. Yes, and we can keep going out as far as we want, as long as everything in the one set is contained in the other. Can we say that set B is a subset of set A? No. Right, there's numbers in B that are not in A. Now here's the tricky question. Is A subset of itself? Mm-hmm. Yes. So it can be a subset of itself. That's all a subset is. Now, this next part is above and beyond. This here, you don't have to write this down, you can just watch this, because again, above and beyond is a number line. Yes? So, a number line, mathematically written, is R1. Real number lines, because real numbers, all the real numbers, yes, are contained on the number line. Well, so XY, yes? Is everything contained on the number line contained in the XY plane? Well, yeah, because it's the x-axis. Now, the x-axis is written as R2. So we can say R1, our number line, is a subset of the graph, yes? Because it's part of the graph. Has anybody seen a graph like this? Because normally, this is not the y-axis anymore. For some reason, they flipped the y-axis down, and up is considered z. But we'll leave it y and z coming out. Is the xy, our graph, a subset of the xyz? Yeah, because everything on the xy coordinate plane is contained in this here, yes? So we can say that this is a subset of R3, our three-dimensional number plane. Yep, so the little c is a subset, yes. Thank you. Pretty good with this so far. So by this logic, we could say that R3 is a subset of R4, which is a subset of R5 or Rn. No matter what dimension, we can say that the higher order of it would be a subset of the whatever we have is a subset of the next one. Continuing on, yes? Do we have a conceptual graphs of R5, R6? No. So Rn, n can be any number. So it goes out infinitum, just infinitely. We can continue this on. Do we have any concept what R6 is, let alone? No, we have no concept of it, but we establish a pattern and we can say it continues on. Again, as I said, above and beyond. Was everybody good at, we were understanding up to R3, R4 we were gone, yes? Yep. Nope, first time I saw that, I was in the same boat. That's it. So, again, we can take subsets all the way to there. All right? Okay, now we're going to bring it back to a little more grounded, something we can conceptualize. Let's look at these subsets. So when we look at this here, we want to write all of the non-empty subsets. I'll explain empty here in a minute. But if we look at 4, 5, again, a subset has to contain everything, or everything in the subset has to be in the main set, yes? So what's one of the subsets of 4, 5? Yes, we can say 4, 5.
4 is a set, 5 is also a set.
Yes. Because we could have the subset of just 4 and the subset of just 5. And we could also have the subset 4, 5. CD, what's one of our subsets? Because we can have the set containing C, the set containing D, and the set containing CD. Three. They both have three. Three subsets. Yes. If you need to write notes on it, go for it. And most have a challenge writing that bracket for the first few times. Another one. Yeah, it's not something that's normally common.
I was slowly just.
Yeah. So another way I've heard is to write an S and then a backwards S. Questions on these two here? Let's look at one that has 3, 2, 4, 6. So let's start, I normally start with 1. Let's start with all the groups of 1. So we could have a set of 2, set of 4, and then a set of 6. All right? But we could also have groups of 2. So 2, 4, 2, 6, and again, I always start with 2, because I start with that first one and do every combination of 2 with it. So we have 2, 4, 2, 6. So that's it with 2, yes? And then 4, 6. Now we're not going to list 4, 2, because 2, 4 and 4, 2 are the same thing. It's just written in a different order. And here, order does not matter. So 2, 4, 4, 2 are going to be the same thing. We don't have to write it twice. So if we listed all groups of 2, well, yeah, there's no other way because 6, 4, 6, 2 have already been listed. Now we can do groups of 3, which is just 2, 4, 6. Yeah, that should be 1, 2, 3. Yeah, that is 7. There should be 7. Yep. You ready for EFGH? I mean, we've gone from what? So 2 had 3, 3 had 7. So 4 should have 10 or so. Let's see. So again, it's easy to start off with E, G. Easy to start off with just groups of 1. I do this just so I keep track of it because the more elements that there are, the more subsets we get. And an element, if I haven't said already, is parts of our set. Each E, F, G, and H would be an element of the set, something contained in it. Let's start with E. So we'd have what? E, yes? G, E, H. So that covered all of them of our 2 elements, 2 parts with E, yes? Then we can move on to what? F, F, G, F, H. Do we have any 2 sets left? G and H. Questions on how we got these subsets so far? F, G, F, H. And then lastly, G, H. Okay, so we've covered all the subsets that contain 1. We've now covered all the subsets that contain 2. So now we're going to move on to all the subsets that contain 3. We will do 4, but we can do 3 first, yes? So our first one would be what? E, F, G. Almost. There's actually more with E. There's E, F, G. E, well, E, G, H, yes. But we also have E, E, F, H. And then E, almost forgot. Because we have E, F, G, E, F, H, yes? Yep. Because we also have what? F, G, H. Yep, because we could switch to G and H, so E, G, H, F, G, F, G, H. And lastly, yes, E, F. The fact that going from 3 elements to 4 changed it from 7 to 15. Imagine if we added a 5th. It's just going to keep getting bigger and bigger. Yes? Questions on these subsets? Now, I did say something earlier, and all of these have said what? Write all of the non-empty subsets. And the reason we say non-empty is because this here is considered the empty set. So a 0 with a line draw through it is the empty set. It's the set containing nothing. Now, it'd be tempting to say, why don't we just put a bracket, 0 bracket. 0 is an element. It is a number. So it's a number, that means, and we have understanding of 0, but we would say it's the set containing 0. The 0 is a number. So it would have something there, technically. Yes. Yes. So, write this. So, now, again, you don't have to write any of this here because it's about to get kind of messy. We could also say the set containing the empty set is a subset of the empty set. Yes? Well, I could also say the set containing the set, and it just becomes endless. Which means if I wanted to list all of the sets, including the empty sets, this goes infinite. I mean, I can write it as many times as I want. So really, any set, the empty set is a subset of it. But we don't worry about those because that just makes things muckier, a little more tricky than they absolutely have to be. Yeah. And again, I didn't learn about the empty sets, or we didn't really talk too much about them until college. So, and that'd be more of a pure math route. But they are something that's interesting to know. Questions on any of this so far? Now, the other thing with sets is we have intervals. And there's 2 main types of intervals. There's bounded and there's unbounded. Bounded means we have 2 endpoints. So there's limited. Unbounded means it's going to be going in one direction or the other. Limitless. Some have a limit. They do have 1 point, but we do have it continuing indefinitely in 2 directions. In geometry, bounded would be considered a line segment. Our unbounded here would be considered a ray. And if it continued in both directions, it would be a line. And as much as I want to say my ray jokes, I will save them for later. Bounded intervals, and I believe this is already filled in years past. I've had y'all fill this, all the writing in. So this first part, let A and B be 2 real numbers such that A is less than B. All this is just, we're talking generic, given any 2 numbers. A is one of them, B is another. And the only thing we're signifying is that A has to be less than B. So if A is 7, B is 9. We're applying it to any number. We're talking about the general sense. Then A and B are the endpoints of 4 different bounded intervals on the real number line. So no matter what A and B, as long as it follows the fact that A is less than B, all of this is going to hold true. Now the 4 that we have, the first one is that A is less than or equal to X is less than or equal to B. We're talking about all the numbers between A and B, and at the 2 points they are equal. Kind of as we have drawn here, I did include that for y'all. Now, as an interval, because we have the inequality, the interval would be bracket A comma bracket. We're saying that A and B are included. Well, on the other end, we can say that A and B are not included. That means we would have parentheses A comma B, parentheses. Because if they're included, we have brackets. If they're not included, we have parentheses. Well, I think we know the other two. One of them we're saying that A, or one side's included and the other side's not, or vice versa. And really, these are the only four types of bounded intervals that we can have, are these here, in at least a two-dimensional plane, yes. Or one-dimensional plane, not two. Two would be x, y. X, y, yeah. Questions on this here? We're good with bounded intervals so far? Yes. Well, if we have bounded, we also have unbounded. Does everybody finish copying here? No? Okay. Again, I will say this now. If at any point I get moving too fast, please interject. So the first one, yes. So the first one is included because our two inequality signs have the equal sign, that equal bar underneath it. So the second one is not. It's not included, just less than. Unbound, or it's still bounded. All four of these are bounded. It's just the second one, whatever points A and B are just not included. We have all the way up to that number, but just not the number itself. So if A was 0, we have all the numbers up to 0. So we'd have 0.00001. A whole bunch of zeros and ones would be included, but 0 itself would not. Any other questions on these bounded intervals? We feel good about these here. The other one is unbounded. Let A be a real number. Each interval on the real number line shown below is called unbounded because we have an endpoint and it continues on either way. Now, I did include one extra, which is really does not have any bounds, but we'll talk about it last. Because we could say that x is greater than or equal to a. All the numbers bigger than or equal to it. So it includes it and goes off in one direction. Or we can just say that x is greater than a. So we have parentheses. So from a to infinity. And in interval notation, smallest number is always on the left, biggest number is on the right. And we'll go on and look at these last two here. X is less than or equal to a, and x is less than a. So we have negative infinity, parentheses, negative infinity, comma a, negative infinity, comma a, parentheses. So again, if we are going to have parentheses, it means it's not included. We have brackets if it is. Questions on this here? That's not us quite yet. We're something like middle school. Yes. Questions on this here so far? We do have this. The only other one that we have left, negative infinity to infinity, is just the whole real numbers, all the real numbers. Now, we're not going to finish the notes, and I did not plan on us finishing the note sheet today. I'm also going to give us some time here in a minute to get logged into Google Classroom, get you all logged in there. But there is one thing I want to talk about before we get there, and that's infinity. Because you guys have an understanding, an idea of it, but there is a reason we do not put a bracket next to infinity. And part of that is because we can never actually get to infinity. Infinity is not a number, it is a concept. And it gets a little bit gray because we feel like it should be a number. We know we talk about infinity, but it's not actually a number. It is just a concept that we have. Most numbers that we have are concepts. And there's different ways to get about this, but I think this is the easier one, and you don't have to write this down. And it's called the infinite hotel. And again, there are videos. I mean, we're in the digital age for sure, more than we were 10 years ago, but there are tons of videos on this infinite hotel. Now, the concept behind the infinite hotel is that there is a hotel with infinite number of rooms. Infinite, infinity. And all of them are full. Now, you being the clerk and wanting to do a great job, make sure that everybody is accommodated if someone needs accommodation or needs a room, someone comes up to you and asks for a room. But again, all the rooms are full. You have to come up with a way to try to get him a room. And you come up with this idea. You tell the person in room 1 to move to room 2. 2 goes to 3. 3 goes to 4. 4 goes to 5. So on and so forth. And everybody is adjusted down one room. Again, it's infinite. So there are infinite number of rooms. They're all full. We moved everybody down one, yes? So room 1 is now empty, yes? So a new guy goes into room 1. And we just make a bigger version of infinity. Yes. It's always filled. Yes. I remind that so the last guy goes to the next room because, again, there are infinite. It is exceedingly bigger. Yes? Because there's an infinite number of numbers. It's just huge. Now, that's just one. This is infinite hotel A. We also have infinite hotel B. In a tragic situation, hotel B burns to the ground. But everybody made it out safely. But, again, you're wanting to accommodate. Infinite hotel A is now going to try to fit in hotel B. And again, every room in B was full, and every room in A is full. So, hey, let's kind of use the same trick similar to what we did before. 1 is going to move to 2. But room 2 is not going to move to room 3. 2 is going to go to 4. 3 is going to 6. 5 is going to 8. All of them are going into the next even number. Well, how many even numbers do we have? Infinite. There's an infinite number of even numbers, yes? So now that that's done, all of the odd number rooms in Hotel A are now empty. And how many odd numbers do we have? Infinite. So that means everybody that was in Hotel B will now move into the odd numbers in Hotel A. Well, now we just made a really bigger version of infinity, yes? A little bit. But is there any way that I can really get to infinity? No. Oh yeah, they get up to nth number of hotels. We can have nth versions of hotels, and they will all merge into one. But there's more trickier kind of ways to get there. But again, I do this. Yes. So that's kind of just showing that infinite is not obtainable. Now, go on and grab